In part 2 of related rates, I'm going to look at another typical problem. This is a problem of an inverted cone. Water is draining from the cone at the rate of 5 cubic centimeters per minute. We're given the overall dimensions of the cone, the depth and the radius at the top, and we're to find the rate at which the water level is changing at a depth of 10 centimeters. So if you take a look at what we've been given here, this is dV dt, rate of change of volume with respect to time, and we're supposed to find the rate of change of depth or height, which is the variable we're using here. So here's my drawing. The overall dimensions of the cone, radius is 15, the depth is 30. We're given the rate of change of volume in terms of cubic meters per minute, and we have to find the rate of change of height or depth when the h is 10. Now you see I have two similar triangles here, and the reason I have to use these similar triangles is that the volume of a cone involves both the radius and the height, and I can't leave both of those variables in there. I'm interested in finding dH dt, so I have to get rid of the r value. If you look at the similar triangles, the ratio of r to h is the same as 15 to 30. So I reduced the 15 to 30 to 1/2 and multiplied both sides by h and got a substitution for the r. r is now h over 2, and I put that in here in place of the r. And you see when I square the h times the h, I get h cubed. Squaring the 2 on the bottom times the 3 gives me the 12. So this is my formula for volume, simply in terms of height or depth of the cone. Now when I go to take the derivative of that, this is again implicit differentiation. I'm taking the derivative with respect to time. So when I take the derivative of this, 3 times that gives me the quarter pi h squared, but then I have dH dt on the end. And at this point I'm going to substitute in the rate of change of volume, which is -5, and I'm substituting in the 10, which I was given up here, and my only variable is the dH dt. So at this point, basically what I did here, I cross-multiplied 4 times the -5 and divided by 100 pi, because that's what I got up here. And if you want to leave the pi in at the rate of change of height with respect to time would be -1 over 5 pi. I just reduced that fraction. The negative indicates that the level is falling at that particular rate. The other problem I want to look at in this video is, again, the typical ladder problem. We have a ladder leaning against a vertical wall and the ladder slides down. We were given the rate at which the foot of the ladder is moving out from the wall, and we have to find out how fast the top is coming down under two conditions: when the bottom is 6 meters from the wall, and then secondly when the top is 6 meters above the ground. Now we're given dx dt, that's the rate at which the foot of the ladder is moving out from the wall, and we have to find dy dt. And to get started, we just use the Pythagorean theorem, x squared plus y squared equals 10 squared. Again, we take the derivative, it's implicit differentiation. I spelled it out with the Leibniz notation here, dx dt on the end of each of these. And as usual, I change to the prime notation because it's just easier to write. So I divided everything by 2, changed to the prime notation. I'm looking for y prime, so I moved the xx prime to the other side, picking up a negative, and then divided both sides by y. So if I have this information, I can find out y prime. Now, the first problem was when the foot of the ladder was 6 meters out from the wall. So I just went back to the Pythagorean relationship here. put in the 6 for the x, 36 from 100 is 64, and so the y value is 8. So I've got all I need to plug into that formula that I've developed up here. Here's my x prime 4, which I was given. This is the x and the y value. The -3 indicates that y is getting shorter. Of course, if the ladder is sliding down, the length of y will be decreasing, and that's why the negative shows up here. Part B, very similar to what I did over here. I just said when the foot of the ladder is 6 meters from the wall, then the 6 would go in for the y, and we'd be solving for the x. Again, it's a 6 and an 8. It's just that they're in, this time the 8 is in for the x, and the 6 is in for the y, and we get a different rate. Now, one thing I should mention here, these units were in meters, and these rates were in centimeters per second. And usually you have to unify units in a question, but you see, in a case like this, whether I have 800 over 600 or 8 over 6 is not going to change the value of the answer. So it is possible in certain cases in mathematics to work with different units. And this is one of them, because you see on the top we have meters, on the bottom we have meters, they cancel out. The 4 is in centimeters per second, so then the answer comes out in centimeters per second.